In section 6.4, we're looking at a general approach to factoring. Our objectives are to factor out any common factor, factor binomials, factor trinomials, and factor polynomials of more than 3 terms. This is basically a review of the previous sections in Chapter 6. A polynomial is completely factored when it is written as a product of prime polynomials with integer coefficients. When you're factoring a polynomial, your first step is to factor out any common factor. The first thing we're looking for is the GCF. Step number 2 is to look if the polynomial is a binomial. If it is a binomial, you want to check to see if it's a difference of squares, the difference of cubes, or the sum of cubes, and use the appropriate model formulas to factor. If the polynomial is a trinomial, we want to check to see if it's a perfect square trinomial. Or if the polynomial has more than 3 terms, we can try to factor by grouping. If any of the factors can be factored further, we want to do that, and then step number 4 would be to check the factored form by multiplying. Let's look at the examples on this slide. Our first polynomial is 9p plus 45. We have 2 terms, so what we can do is determine if there's a greatest common factor. The largest factor that goes into both 9 and 45 is 9, so you can factor out a common factor of 9. When you're just taking out a factor of 9, you're dividing each of those terms by 9. 9p divided by 9 is p, and 45 divided by p is 5. 45 divided by 9 is 5. So in factored form, the polynomial can be written as 9 times the quantity p plus 5. The check step would be to use the distributive property. Multiply both terms by 9 and you would get 9p plus 45. Looking at the second polynomial, we have 2 terms. See if there's a greatest common factor that you can take out of either one of those terms, the GCF. Notice the coefficients of 8 and 4, the greatest common factor of the constants, or the coefficients, is 4. Both have a variable m, so you take out the smallest exponent of m. Both have the variable p. So the greatest common factor is 4mp. If we take out 4mp from both of those terms, we end up dividing out 8m squared p squared divided by 4mp. 8 divided by 4 is 2. M squared divided by m is m. P squared divided by p is p. Divide 4mp, the second term, by 4mp. 4 divided by 4 is 1. M divided by m and p divided by p will simplify. And our final polynomial in factored form can be written as follows. The check step can be found by distributing 4mp times 2mp, and that will give you 8m squared p squared, and 4mp times 1 is plus 4mp. In the last example on this slide, we notice that we have 2 large groups. We have the first group of 5x times the quantity a plus b, and the second group is minus y times the quantity a plus b. These both have that common factor of a plus b. So that is something you can factor out of both of those large groups. And what's left is found by dividing out that a plus b factor, and you would be left with 5x in the first group and left with minus y in the second group. This is our answer in factored form. Now you can work to see if you would end up with that by distributing. The check step would be multiplying the whole a plus b times 5 and the whole a plus b times y. So a plus b times 5x can be written as 5x times a plus b, and a plus b times y, you can write it as minus y times a plus b. On this side, we're factoring binomials. When you have a binomial, you want to see if it's either a difference of squares, a difference of cubes, or a sum of cubes, and apply the appropriate formula. The first one looks like the difference of 2 squares, so we want to be able to write each one of these terms as a perfect square. 64 is the same thing as 8 squared. So we can write the first term as 8m, the quantity squared. 9 is also a perfect square, so we can write this as 3n, the quantity squared. And this looks like a difference of two squares with a basic formula of x squared minus y squared factoring into x plus y and x minus y. So in factored form, 8m plus 3m is the first factor, and 8m minus 3n is the second factor. This is how we write our polynomial in factored form. What you can do to check is use the FOIL process and do the first, outer, inner, and last. When you multiply the first, you get 8m times 8m, which is 64m squared. The outer is 8m times negative 3, or negative 24mn. The inner is plus 3n times 8m is plus 24mn. And the last term is plus 3n times minus 3n, or minus 9n squared. The outer and the inner terms are opposite, and this simplifies to 64m squared minus 9n squared, the difference of two squares. The second example, 8p to the third minus 27, looks like the difference of two cubes. 8 can be written as 2 to the third power, so this first term can be written as in parentheses 2p to the third power. 27 is also a perfect cube, and that can be written as 3 to the third power. Now the basic model equation for the difference of two cubes, if you have x cubed minus y cubed, the first binomial factor is x minus y, and then the trinomial factor is x squared plus xy plus y squared. So in factored form, our difference of two cubes here, the first binomial factor will be 2p minus 3. The trinomial factor, we'll take 2p and square it to get 4p squared, plus x times y, that's going to be 2p times 3, or 6p, and then the y squared plus 3 squared, which would be 9. This is our final answer in factored form. Starting off with a difference of two cubes, the binomial factor is 2p minus 3, the trinomial factor is 4p squared plus 6p plus 9. On this slide, we're looking at the first polynomial as 1000m to the third plus 1. This looks like the perfect a sum of two cubes. So recall that the formula for the sum of two cubes in factored form, x cubed plus y cubed, can be written as x plus y times x squared minus xy plus y squared. So we want to be able to write both of these as perfect cubes. 1000 is the same thing as 10 to the third power. So the first term can be written as, in parentheses, 10m to the third power. And 1 can also be written as 1 to the third power. So this follows that model equation. Our factored form can then be 10m plus 1 as your first binomial factor. And if we square 10m, we get 100m squared minus 10m times 1, or 10m, plus y squared, or plus 1. So we have our polynomial written in factored form. The second example here isn't a sum of cubes or difference of cubes. It looks like we have a perfect square and a perfect square. Now the only formula we have that involves perfect squares is if we have an equation, or a polynomial, that's written in the form of x squared minus y squared. Then we know the factors are x plus y and x minus y. There is no special formula for x squared plus y squared. We consider this to be prime, and it cannot be factored. So although it looks like it could follow this model formula for the difference of two squares, The fact that we have a plus sign in between means that this is prime. It cannot be factored. On this slide, we have three polynomial expressions that we want to factor. In this case, they're all trinomials. The first one, p squared plus 10p plus 25, is considered to be a simple trinomial. So we can look at the last term and list the factors of c that will add up to the middle term. 25 can be written as 5 times 5, 1 times 25, negative 5 times negative 5, and this pair of factors, 5 times 5, will add up to give you the middle term. So this can be written in factored form as p plus 5 is one factor and p plus 5 is the other factor. Another way to write this, since those factors are identical, would be p plus 5 squared. This is an example of a perfect square trinomial. The first term is a perfect square, the last term is a perfect square, and that middle term is twice the product of the first and last before you square it. This second example also looks like one of those perfect square trinomials. And recall, if we have x squared minus 2xy plus y squared, that this is considered a perfect square trinomial that can be written as x minus y squared. So we can write 49z squared as 7z to the second power. That's a perfect square. The last term, 9, can be written as 3 squared. If that middle term can be written as minus 2 times x times y, or minus 2 times 7z times 3, then it falls into this form of a perfect square trinomial. And 2 times 3 is 6, and 6 times 7 is 42, so this is equivalent. It follows that form for a perfect square trinomial, and the factors can be written as 7z minus 3 and 7z minus 3, which can also be written as 7z minus 3, the entire quantity squared. This is our answer in factored form. For the last example, we have y squared minus 5y minus 6. This is considered to be a simple trinomial. We want to look at the factors of the last term c and find out which pair of factors will add up to the middle term. So negative 6 can be written as negative 1 times 6, negative 2 times 3, negative 3 times 2, and negative 6 times 1. We're searching for the pair of factors that will add up to the middle term. Because negative 6 plus 1 gives you that middle term of negative 5, those are going to be used in our factors. Our one factor can be written as y minus 6, and the other factor y plus 1. This is our answer in factored form. And you can always check these by doing the multiplication to see if you get back to the original polynomial. Let's factor 2k squared minus k minus 6. This is a trinomial, but it's not considered a simple trinomial because the leading coefficient a is something other than 1. So let's use the AC method to factor this trinomial. Remember that the AC method first involves taking the value of a, which is 2, so a times c, and multiplying by c. So that is going to give you 2 times negative 6, which is negative 12. Now we list the pairs of factors of negative 12, which is negative 1 times 12, negative 2 times 6, negative 3 times 4, and so on, negative 4 times 3. And you want to find the pair of factors of negative 12 that will add up to the middle term of negative 1. And I see, without going further in the list, that this pair of factors, negative 4 times 3, gives you negative 12. That gives you AC. And when you add negative 4 plus 3, you get negative 1. And that's the middle term. We are going to then split the middle term, leaving the first term as a 2k squared. The last term, leave it as a minus 6. But that middle term we're going to separate into two terms one of them being minus 4k and the other being plus 3k. Now we factor by grouping. Look at the first group and determine what is the common factor. The common factor here is 2k. When you factor out 2k, you're left with k minus 2. Look at the second grouping here, the plus 3k minus 6. The greatest common factor here is plus 3. When you factor out the plus 3, you will be left with k minus 2. Now notice that k minus 2 is common in both larger groups. So in factored form, this can be written as k minus 2 is the common factor in both of the larger groups, and when that is factored out, the result is 2k minus 2. So in factored form, k minus 2 is one factor and 2k minus 2 is the other factor. You can check this by using the FOIL process to determine if you get to the original trinomial. Let's look at the next example here. We have 28z squared plus 6z minus 10. I do notice that all of these terms, 28, 6, and 10, are even numbers. So I know right away there's a greatest common factor of 2. I'm going to divide out 2 before I bother to factor the trinomial. When you factor out that greatest common factor of 2, you get 14z squared plus 3z minus 5. Now the trinomial that we have in the parentheses here is not a simple trinomial, so we can use the AC method as well. AC in this case, where A is 14 and C is negative 5, ends up giving us a quantity of negative 70. Now I need to list all the pairs of factors of negative 70 that will add up to a positive 3. There's quite a few pairs of factors there. By trial and error, you can find the first pair of factors is negative 1 times 70. That's definitely not going to add up to 3. You can do negative 2 times 35, and so on. It looks like the pair of factors that add up to positive 3 would be negative 7 times a positive 10. Negative 7 times a positive 10 does give you negative 70, and negative 7 plus 10 does add up to a positive 3. So we are going to split that middle term, keeping the first term as 14z squared and the last term as minus 5, and leave that 2 out in front. 14z squared, the first term we're going to keep it as 14z squared, the last term we keep it as minus 5. We split that middle term into a minus 7z and a plus 10z. Looking at the groups here, the first group has a common factor, the last group has a common factor. Let's work on factoring those out. Keeping that 2 out in front, the common factor that you can take out of both 14z squared and minus 7z, the common factor is 7z. When you take out the common factor of 7z by dividing by 7z, what you get here is 2z minus 1. Looking at the last two terms, it has a common factor of 5. Taking out a plus 5 there, because that sign is a plus, and the remaining polynomial there, 10z divided by 5 is 2z, and 5 divided by 5 is 1. So notice here that we have 2z minus 1 and 2z minus 1, what they have in common. And then out in front, 7z, out in front here, 5. So our factored form can be written as 2 as that single greatest common factor that we took out from the beginning, the factor of 2z minus 1, and the factor, when you take out the 2z minus 1 from both of those, the remaining factor is 7z plus 5. This is our polynomial written in factored form. All right, for this example, we're factoring polynomials with more than 3 terms. If you printed out the lesson pages, there may be a mistake. Just check to make sure the polynomial is 20k to the third plus 4k squared. That squared might not have appeared on your lesson plan. Minus 45k minus 9. Now, you want to first find out if there's any greatest common factor of all 4 of those terms, and I don't see any. So my strategy is, when I have 4 terms, is to factor by grouping. I look at the first group, find out what they have in common. I look at the last group, find out what they have in common. In the first group, it looks like there's a common factor of 4k squared. If I factor out 4k squared from the first 2 terms, dividing 20k cubed by 4k squared, I get 5k. And 4k squared divided by 4k squared is 1. Looking at the last 2 terms, looks like there's a common factor of minus 9. Taking minus 45, dividing out a negative 9, and that's going to give me 5k. And that negative 9 divided by negative 9 is a positive 1. Now I'm looking at these 2 larger groups. First group here, last group here. Notice the common factor of 5k plus 1. That is one of the factors, 5k plus 1. The other factor, what you see before those common factors, we have 4k squared minus 9. Now you may think that this is in completely factored form, but let's take a closer look at the second polynomial factor. 4k squared minus 9. That you should recognize as a difference of 2 cubes. Remember that x squared minus y squared can be factored into x plus y and x minus y. So 4k squared, that's a perfect square, and 9 is also a perfect square. So think of this second polynomial, or second factor, as 2k squared minus 3 squared, and we're going to apply the formula. So our first factor is still 5k plus 1, and then in factored form, and the other factors are 2k plus 3 and 2k minus 3. So this is your polynomial in completely factored form.